Section 4 is complex numbers. A quick word about kind of what I expect us to do with them. You can see the objective just says to do operations. You could add to it to do some solving. You'll kind of see in the last slide today as far as we'll go with them. I'll tell you right now, very unlikely that I'll give you any kind of application question that involves them. So I'm really not super concerned about that. What I am concerned with is that you know what they are, the basics of their operations, how to use them, and somewhat of a sense with the solving component as to when you can see them when you're working with polynomials and why they come up. Quick discussion about good old I and where does it come from. It actually comes from a relatively simple question. What is the square root of -1? The real number line, where we spend the vast majority of our time, which is right here, does not have an answer to that question as to what is the square root of -1. Okay, I highlighted the real number line because that's our favorite. It's where we do most of our business, most of our damage, if you will. We're almost always dealing with real numbers. But a couple patterns that show up with imaginaries, right? Because together with the reals, they form what's called the complex number plane, which if you're going to really get into the application side and rely on the complex numbers, you're getting to a pretty high level of math. It's pretty sophisticated stuff. You can go all the way up through, Precalc and calculus, really, and you don't really need to use them all that much. Which is why our focus right now is just you should know what they are and know the basics of how they work. Okay? So, again, the square root of -1, that's I. That's where it comes from. A couple other things I want to show you. For example, I squared, which would be the square root of -1 times the square root of -1, or just -1. That particular, I put that on the very first slide because this one just seems to come up over and over again, that we use the fact that I squared is -1. We could look at I cubed, which a good way to look at that would be I squared times I to the first. Or just -I. And my personal favorite, good old I to the fourth. That's like I squared times I squared. If you look back to I squared, that's -1 times -1, or just 1. I squared and I to the fourth I especially like to talk about right away, just so you get the sense that imaginary numbers aren't like this completely different set of numbers. Okay, they're very much related to real numbers. Like I to the fourth power is the same value as 1. When you're working with polynomial expressions, a square root of a negative can come up, and to yield some answers, we need to rely on a kind of a modified number system, but they're related to real numbers. Now, if I were to plot this point right here, I could see that 1, 2, 3, 4, 5 is the real component, and 1, 2, 3, 4, 5, 6 is the imaginary. So you're going to see our answers expressed today like this: 5 plus 6i. And we're going to deal with a lot of numbers that have this real component and they have the imaginary. All right. you'll see such an answer is referred to as standard form, and that's what you're looking at for most of our problems, is to get something like a plus bi, where you've got this real and this imaginary component. If you get your answer to that form, that's kind of what we're looking for. All right, so the next few slides, what I want to take you through is just some of the basics of the operations. Add, subtract, multiply, and divide, more or less is what I want to do. Okay? And here's what I always say with dealing with numbers that involve I. Be really clear that I is not a variable. Okay? But if you kind of want to, when you're doing operations, if you want to pretend it's one, that's okay, because it follows the exact same properties. Okay? Here, when I'm adding them together, this problem basically just becomes a whole bunch about like terms. Right? 4 plus 1 is 5, and 7 minus 6 is just 1i. 5 plus I. That fits the form that we were talking about. Right? The real component is 5, the imaginary component is 1. Those two complex numbers added together give you 5 plus I. Okay? But you can treat the numbers in the sense like, like the real numbers are like terms and the imaginary components are like terms. That'll work. That you can combine the imaginaries and the reals, but you can't combine them together. We have 3i. You'll see this come up too, that if you have parentheses with a negative sign in front, those need to be distributed. That'll give me positive 2. There's 3i. And this last set of parentheses, that'll be a minus 2, and then minus a 5i. So it is a lot like just combining like terms. But you got to make sure that your parentheses are taken care of before you combine them. So here when I do that, again, now I'm looking at the i's and I see that, the 3i minus 3i cancels. And I'm left with this minus 5i. And the real numbers, they cancel too. 2 minus 2 is 0. So there actually is what we just call an imaginary number. It has no real component. It's just minus 5i. Okay? Where you saw part A had both. Now, I'm just kind of illustrating that you can get these different types of answers. Adding them and subtracting, it's just not going to vary all that much. It's really like combining like terms. All right? So here, the 3 plus 2i, that's fine. Plus 4 minus I, there's nothing to distribute there. Here we have minus 7, and I do need to turn that into a minus I. And once those parentheses are gone, again, it's just like combining like terms. But this one, and again, this illustrates really well that complex numbers come up in, at least they can come up in polynomials that are really just based on real numbers. So again, they're very much related. So like right here with the reals, you see we have 3 plus 4 minus 7. Well, that's 0. And then we have 2 minus 1 minus 1. Okay, you can have a big expression like that has 3 complex numbers, and you get a real number as an answer. Okay, very, very possible that will happen. That whole expression right there simply, it simplifies to 0. All right, let's look at multiplying. The slide is multiplying, and then a little look at dividing complex numbers. Okay. As you look at that, maybe, just maybe, it reminds you of like a FOIL. I'm going to give you a heads up here. I would put up at the corner of your paper somewhere to keep this in mind. That's just not going to go away, that I squared is -1. We'll use that a lot. But if you look at this expression and kind of think like, hey, is this like a FOIL? Yeah, it's a lot like a FOIL. Okay? That would be my first step, is to take the four times 2 to get 8. Oh, and then we'd have plus 6i minus 4i. Now things at the end here get a little bit interesting, because that we're used to. Like we've got reals, we've got imaginaries, all right? Then it becomes like this combining like terms. But at the end here we get minus 3i squared. Because we are going to be picky that our answers are in that form a plus bi, but how do we deal with this whole I squared thing? Use the fact that I squared is -1, and if you were to do that, okay, the 6i minus 4i could be combined into 2i, but when you make that substitution with the -1, that last term becomes plus 3. 8 plus 3 is 11. (11 plus 2i fits the form of the answer that I'm looking for. Okay, so that will come up repeatedly, particularly if you're multiplying. How about a complex number multiplied by itself? About the only thing that this one adds is this process where you should take the number and, just to make sure that you do a FOIL, write it out, so it looks like any other FOIL where you have that complex number multiplied by another one, because then you're more likely to treat it like any other problem. You get 9 plus 6i and then again, you're going to see this come up every time with this last term, that we get plus 4i squared. And if we make that substitution with -1, this would become 5 for the real component, and then of course we have two 6i's, which would be combined to be 12i, which fits standard form, and that's the answer I'm looking for. Here's just a complex multiplied by a real number. Not a lot of, crazy stuff going on here. The 4 needs to be distributed, and we'd get -8 plus 12i. Those terms can't be combined. It's in our standard form, and that's that. Okay? If you kind of stick with the FOIL approach and use the fact that I squared is -1, there's not a whole heck of a lot to these operations. They're not really all that bad. Here's probably the most tedious one, though, is dividing. It kind of seems like at first you're like, why would you do this? We need to use something called a complex conjugate, because something kind of cool happens if we do that. Cool in the sense that it's going to help us, simplify this problem. Whenever you see that term a conjugate, you're talking about the same complex number, just switch the sign in between them. Okay, so now what this is all about is, I'm going to multiply this, but it has to be the same number. on the top and the bottom. I'm going to use 4 plus 2i. That's not just some random complex number I picked. It's the conjugate to the number that's on the bottom. Okay. Now I hope when you see this that you're thinking not just like foiling, that it more or less kind of becomes like a superfoil, you know, on the top and on the bottom. Now the conjugate thing probably seems pretty random, like okay, whatever, I get it, but what are you doing? Hold on for a minute and let's stay focused on the denominator, and you're going to see something kind of nice happens. That's always going to happen if we use a conjugate. I'll start with the top though, because I got to FOIL both. There we'd get 8 plus 4i plus 12i plus 6i squared. Don't forget about I squared being -1. Okay? I'm going to fix this one real quick. All right. We'll worry about simplifying that in a minute. Let's just keep going, though, and let's FOIL the bottom. I get 16 plus 8i minus 8i. Ooh, look at those two i's. Same quantity, opposite sign. I wonder if that's a coincidence. It's not. Has a lot to do with the whole conjugate thing. Minus 4i squared, and again we're going to have to use that I squared thing on the bottom too. It's pretty common if we multiply it all. Alright, let's just look at the whole top here. That last term when I put in -1 is going to be -6. So the real part is just going to be 2. And then with the imaginaries, it's going to be plus 16i. On the bottom, again, the i's will cancel. This is, again, the conjugate thing. And we end up with plus 4, and look what happens down to the bottom is we get just 20. So if you take two complex numbers that happen to be conjugates, it guarantees you're going to get a real number as an answer. And as far as getting it to standard form, I wanted that. Okay, that's what I was looking to have happen. Now you can see here I'm getting really, really close to my standard form because there's my real component, 2 over 20. Here's my imaginary component, 16 over 20. And of course there I have to stick an I with it. And hopefully you're thinking, well that's great, but just hold on just a minute. 2 over 20, oh that's so much better, 1 over 10. And 16 over 20, how about 4 over 5? Now this one, gave us a final answer with fractions, but that's fine. We got to the same answer where it's a plus bi. A is your real component. Here it's 1/10 or 0.1, and the imaginary component was 4/5 or 0.8. Right? So it fits, again, with all of these operations, the right form of the answer that I should get. Now, what if you come across some problems like these? Because these can kind of freak people out, but they're really important because if you come, like within a polynomial, if you come across an imaginary number, it's probably going to be something like this. Because that's, again, the whole reason they come up is we can be stuck if we're solving some polynomials, especially finding some zeros. We could get the square root of a negative. All right, so what we got to do is we got to figure out how to how to handle this, right? Because all those other problems we just did, the i's were already there, and when you come across this with a polynomial, that's not going to be the case. So here's what I'd like to do. Okay, really, if you look at the square root of 3, here's what's happening. I'm not going to write these steps out every time, but that's really the process we need to go through, is to get it split up. Get the negative out of the square root, okay? And then, of course, the square root of negative 1 is I. So the way you'll hear me refer to it here is, okay, you see the square root of negative 3? Just make it square root 3, okay? Which is fine so long as right at the end, make sure to tag on an I, because that's the same thing, okay? So this is like the little conversion that you need to make is, okay, now we have a positive square root, that's fine. Just make sure to have I with it. It's like a little trade-off. And now it starts to look like all the other problems that we've been practicing. Square root of 36 times I squared. Again, remember what I said about I squared. It just shows up again, again, and again. That's negative 1. Square root of 36 is 6. It's negative 6. Okay? Which, again, you can have two imaginary numbers, multiply them, and get a real number as an answer. Okay? Now, this one actually involves some subtraction, so it's going to look a little bit different, but really the thing I want to focus on is this first step, that to get going, you need to get that switched over to a 48. Just put an I at the end. Square root 27. Okay. Now they're both i's, so it's almost like I've got my like terms here, and if I'm subtracting them, I'd like to combine them. I'm dealing with some square roots, and I can only do that if I can get them written as the same square root. Okay? What I have to look for is, do I have any perfect squares, like any factors of 48 that are perfect squares? Okay, and there's no guarantee I can combine these two terms. I'm just checking. It's very possible that they can't be. Now, it's an example that's going in your notes, so I want to show you the process. So this happens to be one where we can. And the way I would split that up is, 48 can be split up as 16 and 3. Well, the square root of 16 is 4. So I'll carry that down. Again, that's coming from square root 16. Square root 3 can't be simplified, and it's still with the I. So what I'm checking for now in the 27 is, can I also split it up so that it's written as square root 3? And this is one where I'm in luck, because I can split up 27 as 9 and 3. This could be 3 square root 3 times I. Now that they have the exact same square root, I can treat them like terms. 4 minus 3 is 1, so I really have 1 square root 3i. All right, on part C, okay, here's what I would do to write out this one. It's going to kind of turn into a FOIL, but right away I'd say, okay, negative 1 plus, if I'm going to actually do the operation here, I don't like that written as square root negative 3. I would much prefer square root 3i. And then, of course, have the same thing, negative 1 and from there, it's kind of like a FOIL. I would get 1 minus square root 3i minus another square root 3i. Now, keeping in mind, I'm looking ahead to simplifying. Those two I can combine. They both have i's, and they both have the exact same square root. Plus the square root of 3 times the square root of 3 is just 3. And yet again, good old I squared shows up. Put in the -1, and our last term becomes -3. 1 minus 3 is -2. And now it looks like with this square root 3i, I had -1, and I took away another one. That gives me -2. A real component of -2 and an imaginary of -2 square root 3. Kind of interesting numbers, but they fit the form that we should get for our answer. Okay. Now I said at the beginning I would give you a couple examples to finish with that are like as far as I would have you go with this complex number stuff, because from the very beginning I said we're going to have some limits. Word problems that involve them are very likely going to stay off limits. But I do want to give you some kind of sense of where they come from, right? I've got really the parent quadratic function just shifted up 4 units. All right, I'm just finding some zeros. And I get this. And then I undo this square, and I get plus or minus the square root of -4. Okay? Now, in the process of looking for these zeros, I'm going to run into some complex or imaginary numbers. Now, the plus or minus needs to stay there because that's coming from the square root. This is what we were looking on the previous slide, is just take the negative out. Throw on an I, though I do want to make note on this step. I see this come up all the time, that when you insert the I, for some reason, and I don't really know why, for so many, the square root all of a sudden just disappears and we end up with plus or minus 4i. At that point, it's still there. Then I can take the square root and I get plus or minus 2i are the only solutions, the only two solutions to that equation. Now that would tell me a little something if I'm thinking about the graph. And I was looking for zeros. This was a parent function that had been shifted up 4 units. So if I'm looking for zeros and I get just imaginary numbers, there's a little hint that as far as real zeros, like where we would actually see the graph cross the x-axis, this one doesn't have any, right? It's not a quadratic that ever does. And even if you had an application problem where you're like, in this application problem, even though we're not going to do those, that we're looking for where, this quadratic or this polynomial crosses the x-axis, if you just got imaginary solutions, you'd be like, wait a minute, it actually doesn't. That could mean a variety of things. You could go back to that, polynomial you had if it was an application, and you'd look at it again thinking, if you were really expecting to find an x-intercept and didn't, who knows where that would go. But it's an interesting case. All right, let's look at one more that's just a little bit more complex. Same idea, though. I've got a quadratic, and at first it's kind of like, okay, 3x squared minus 2x plus 5. Let's find some zeros. Okay. And you might think, all right, go ahead and try to factor it. All the coefficients seem relatively small. This shouldn't be too bad to factor. You're not going to have any luck, right? Because we are going to end up with some imaginary solutions, because the same thing is going on. That if you were to try to factor this, you're trying to find your x-intercepts or your zeros. This one doesn't have any, and what's going to tell you that is it's going to have imaginary solutions. Now, you maybe already have a sense of where this is going. A is 3, B is -2, and C is 5. And if factoring doesn't work, we've seen this before, that this is our next option. just getting all the numbers plugged into the quadratic formula. And now you can see here, with the structure of this formula that, where could we possibly run into imaginary numbers in our solutions? Well, this has a huge square root in it, and what if that square root comes out to be negative? Because if you were to go ahead and simplify that, you would see all those numbers underneath the square root. They come out to be negative 56. All right, now if I'm thinking about this quadratic and its graph, that's telling me right off the bat that this would tell me x-intercepts. This one doesn't have any, right? The graph doesn't actually cross the x-intercept because I'm going to get imaginary solutions here. But I'm still going to finish it out and get the solutions. My next step would be, let's do square root 56. Notice I made it positive, and there we go. Now I have an I. The 56, I want to kind of do the same thing I did on the previous slide when I had the problem that involved square root 48 and 27. Any factors that are perfect squares, and there is 4. 4 times 14 is 56. Now the square root of 4 is 2, so that'll get multiplied by square root 14. The I is still there. This is starting to look like the form that I want my answers in, except I'm going to tweak one thing here. How about this? Shifts to a third, and over here, which we could give our final answer here as 1/3, that's the real part, plus or minus square root 14 over 3, and of course, don't forget the I to go with the imaginary component. So there you've seen it. You've seen it all. Add, subtract, multiply, and divide. Know some of the basic properties, and maybe even solve some polynomials that give you imaginary solutions. That's kind of what we're looking for in Learning Target 4.